Hey guys, and welcome to another A-Level Maths revision video. And in this video today we're doing something a little bit different. We're actually going to walk through what I've put together as a predicted paper 1. So just to make it clear, this paper has got no affiliation to any exam board in particular. I've based the questions on old Pearson Edexcel exam papers. You should find this paper helpful if you're doing pretty much any exam board, AQA, OCR, but it has Edexcel in mind. That's the aim of this paper. So the questions in this are all from old exam papers, from the old C1 to C4 papers, and a few questions from the new papers, and including the topic tests that have been released by the exam board to help you. So this is all using the advanced information. Pretty much every topic that was mentioned on the paper 1 you will see in this paper and video. Like always, I'd love to hear your feedback regarding the questions, if you make it all the way to the end. How did you find the paper? Hopefully it wasn't too easy, it wasn't too hard, but hopefully a nice balance of easy and challenging questions. So that should sum everything up. So let's jump into this predicted paper 1 for the A-Level Maths exams for 2022. So starting with question 1 here on this A-Level Maths predicted paper, we have a question here on small angle approximations. So quite a nice question just to get us started. So we're told that theta is small and measured in radians, and we're asked to use the small angle approximations to show that 4 sine theta over 2 plus 3 cos squared theta is approximately a plus b theta plus c theta squared. And a, b and c are integers that we need to find. So in the top right corner here, I've included the part from the formula book here for Edexcel, which gives you the small angle approximation. So this is in the formula book. Do use it to help you. You don't have to memorize these results. So what we've got here, if we just write this out, is 4 sine, so 4 sine theta over 2. We have plus 3 cos squared theta. Okay. So what we need to do here is just use the small angle approximations for sine, because we have the function here of sine, and we also have cosine. So obviously this cosine here is squared, but we don't need to worry about that too much. We'll get to that in a moment when we take a look at the approximation. So we start with the sine theta approximation here, and we notice that this is a sine theta over 2. So we have this coefficient of 4. All that means is we're going to do 4 times the approximation. And the approximation here, well, given that this is sine theta over 2, well, sine theta is approximately theta. So if we have sine theta over 2, then that will be approximately theta over 2. So what we've got here is 4 lots of theta over 2. Okay, so that's the first part there. And now we have this 3 cos squared theta. Now, as this is cos squared, we can refer to our trig identities using sine squared theta plus cos squared theta is equivalent to 1. Then we can rearrange this to be in terms of cos squared theta. So cos squared theta, well, that will clearly be 1 minus sine squared theta. Okay, and what we'll do here is we'll use this result, because it's actually easy just to use this result here. Okay, just substituting in 1 minus sine squared theta, because obviously sine theta is just approximately theta. So in that case, sine squared theta will be approximately theta squared. You can use this result here of cos theta being approximately 1 minus theta squared over 2 and square that and times that result by 3. But the actual working is more complicated. Nothing too crazy, but it makes sense. It's easier just to use this identity here. Okay, so this is going to be plus 3 lots of 1 minus sine squared theta. So we just write that out first. So 1 minus sine squared theta. So again, this will be 4 theta over 2. So we can write that as 2 theta. Here now I've got plus 3. 3 times 1 is 3. So I get plus 3. And then I get minus 3 sine squared theta. Okay, so all we need to do now is use our approximation for minus 3 sine squared theta. So like we just said, sine theta is approximately theta, so sine squared theta will be approximately theta squared. So that's going to be minus 3 theta squared. So what I've got then is minus 3 theta squared. We've got the plus 2 theta, and finally we've got the plus 3. And if we just write in the way that we've been told to express this here then, so what we can say is 4 sine theta over 2 plus 3 cos squared theta well, that will be approximately then. So it's a, so that's just my constant term here, that's the 3, plus b theta, so that's going to be plus 2 theta, and then finally it's c theta squared, so that's going to be minus 3 theta squared there. Okay, and that gets us the first 3 marks there for question 1. Moving on to question 2 now, we have a question here taking a look at vectors. So we're given figure 1, which shows a sketch of triangle ABC. We're given that 2 vectors here. The vector AB is equal to minus 3i minus 4j minus 5k, and the vector BC is equal to I plus j plus 4k. So part A here, so for part A, we're asked to find the vector AC. So let's take a look at part A first. So if we want to simply find the vector AC here, well, we know the vector AB, and we also know the vector BC. So if I want the vector AC, then we need to take the vector AB and add the vector AC. Okay, so that's going to be the vector AB plus the vector for BC. Okay, and we already know these vectors, so this is rather straightforward. So in that case, if I use column vector notation here, so that's going to be minus 3, minus 4, minus 5, plus the vector for BC, which is 1, 1, 4. Okay, so therefore adding each element as we go along, so minus 3 plus 1 gives us minus 2. That's minus 2, minus 4 plus 1 gives us minus 3, and finally minus 5 plus 4 gives us minus 1 there. Okay, so this vector here represents the vector AC. So that's the first part done there. Moving on to part B here then, we're asked to show that cos ABC is equal to 9 over 10. And what I'm going to do here is just quickly clear these 2 lines that I've drawn. So what we're looking for here is to show that the cosine of the angle ABC, so that's this angle here, ABC, so this angle here, we need to show this is 9 over 10, okay? So we're not showing technically that the angle is 9 over 10, but the cosine of that angle is equal to 9 over 10, okay? So how do we do this? Well, to start with, let's actually work out the lengths here, okay? So for example, if we start with AC here, the vector AC, the magnitude of that vector, so the magnitude of AC, that's going to be equal to the square root of minus 2 squared plus minus 3 squared plus minus 1 squared. So I get minus 2 squared plus, like we said, minus 3 squared, and then finally plus minus 1 squared. Okay, and if we evaluate this here, what would we get? Well, we're going to get 4 plus 9 giving us 13 plus the 1, so we get the square root of 14. And we also need the length here, or the magnitude of AB, and also BC. So we're going to work that out for each vector that we have. So therefore, the magnitude of AB, well, that's going to be the square root of minus 3 squared plus minus 4 squared plus minus 5 squared. So minus 3 squared plus minus 4 squared plus minus 5 squared. What would that give us in this case? Well, we actually get here the square root of 50. So that's the square root of 50. And then finally, we also need the magnitude of the vector BC. So the magnitude of BC in this case is equal to the square root of 1 squared plus 1 squared again plus 4 squared. Okay. And if we evaluate this here, what would we get? Well, we're going to get 2 plus 16, giving us the square root of 18. Okay. So what we've got here is everything that we need now to show or find, well, in this case, show that cosine of ABC is equal to 9 over 10. And to do this, as we've got the length here of all sides of this triangle, then all we're going to simply do is apply the cosine rule. As this length here, oh sorry, this point here is labelled as B, this point here is C, this point here is labelled as A. What I'm going to do is do the opposite lengths then. So this will be little a as its opposite capital A. This here will be little b as its opposite capital B. And then finally, this will be little c. Okay. So what we're looking to show here is the cosine here of this angle, what we're going to call B. It's actually ABC in the question, but we're looking for cosine of B. So in that case then, applying the cosine rule here, what we've got is B squared is equal to A squared plus C squared minus 2AC cosine of B. Okay, and that's what we're looking for here at the very end, cosine of B. We're going to eventually rearrange and have that in terms of cosine B. Obviously, this will eventually be cosine ABC, but we'll replace that at the end. So to start with, we know what these lengths are. So the C here, that C represents this length here, so that's the vector AB. So if I just write them up here, so A, B, and C, just so we don't get confused, because I will do if I don't. So A represents the magnitude of BC, B represents the magnitude of AC, and then finally C represents the magnitude of AB. So we just need to use those lengths now, those magnitudes, with the cosine rule here. So B squared, that's the magnitude of AC squared. Well, that's the square root of 14, so if we square the square root of 14, that just simply gives us 14. Okay, so 14 is equal to A squared. So we need to take A here, which is the magnitude of BC, and square that. So the magnitude of BC is the square root of 18, so if we square it, we simply get 18 plus C squared. Well, C squared in this case would be the square of the magnitude of AB. So AB, or the magnitude of AB is root 50, so we square that, we get 50. So you can see the pattern that's kind of forming here. Minus 2AC, so it's minus 2 times A times C. So A is the magnitude of BC, so that's root 18. So 2 lots of root 18 times by, so that was root 18, so that's BC here. And then we also need C. So which one was C? AB, so that's root 50 there. So I'm getting a bit mixed up here. So just a double check here. So minus 2AC, so minus 2 lots of A, which we know is the square magnitude of BC, which was the square root of 18. And then finally C here, which represents the magnitude of AB, which is root 50. Okay. And this is multiplied by cosine of B. At this point here, you can replace that with ABC if you want. So we know here cos B is equal to cos ABC. I'll just put that there just to get rid of any confusion. All I simply need to do here now is rearrange to have this in terms of cosine ABC. Obviously, when we put down the original cosine rule here, we could have rearranged from the start to have that in terms of cos B. That's another way of doing it as well, but I'm just going to take it from here now. So as this is negative here, I'm going to add that to both sides to start with. So I'm going to get 2 lots of root 18 times root 50 cos ABC, and that's going to be equal then to 18 plus 50, so 18 plus 50, and then we minus this part of the left hand side, so minus 14. Okay, so everything looks good so far. And like we said, we need to put this in terms of now cos ABC. That's what we're looking to show here. So all I need to do now is get rid of this part in front. This 2 root 18 root 50. So therefore, cos ABC is going to be equal to 18 plus 50 minus the 14. And the way we get rid of this here is just by dividing. So we divide both sides by 2 root 18 root 50. So we divide by 2 lots of root 18 root 50. And if we evaluate this on our calculator, what we find here is this is exactly equal to 9 over 10 there. Okay? And that gives us part B there and the solution overall to question 2. So question 3 here is a question taking a look at logarithms. So we've been given that the logarithm here of 7y plus 1 base x minus the logarithm of 2y base x is equal to 1. We have these restrictions here that x must be greater than 4 and y is between 0 and 1. And all we're asked to do here is express y in terms of x. So where do we begin with this? Well, the first thing we should always think about when we're dealing with logarithms like this is what rules can we apply? And the first thing I can note here is that we've got the logarithm here of 7y plus 1 base x minus the logarithm of 2y base x. So as these have the same base and we're subtracting, then we can use the quotient rule here for logarithms. So in that case, we can express this as a single logarithm. So this would be the logarithm here with the same base, base x. And as it's 7y plus 1 minus the 2y here, that would be 7y plus 1 as my numerator. So 7y plus 1 as my numerator. And we would divide here by the 2y. Okay, so 2y is the denominator. And this is all equal to 1 still. Okay, so all we've done here is just took the left-hand side and expressed it as a single logarithm. Now here, the first thing I want to do is get rid of the logarithm on the left-hand side. So how do we do that here? So we have this logarithm, this expression, base x. So to get rid of the logarithm, we anti-log, as we would say. And to anti-log, all we essentially do here, in this case, is essentially raise everything to the base. So as this is base x, I do this as x to the power of log 7y plus 1 over 2y base x. And on the right hand side, this will be x to the 1. Okay, if that was 4, it'd be x to the 4. If it were 3, it'd be x to the 3, and so on. So you can kind of see how this works. And the left hand side here, when we anti-log a logarithm, they're almost going to essentially just cancel out. That's what happens here. So the logarithm cancels, and I get left with this expression. So we get 7y plus 1 over 2y. And on the right hand side here, like we just said, this would be x to the power of 1. And we don't need to write the power of 1, but I will write it here just to make it clear what's happened to this one. So that's x to the power of 1. And we're looking to express y in terms of x here. So at this point now, this boils down to a pretty basic rearranging problem now, where we're looking to make y the subject. So first thing I'm going to do here is multiply both sides by the denominator of 2y here. So I get 7y plus 1. And that's going to be equal then to 2xy. Okay, that's x to the 1 times by 2y, we get 2xy. And clearly then in this case, all we need to do here now is get the y's on one side and factor out the y. So therefore, I can do this as 2xy. I'm going to minus the 7y here off this side. Minus 7y is equal to 1. And like we just said, if we factor the y out then, so we factor the y out here, I get y lots of 2x minus 7 is equal to 1. And then clearly, we just want y here to express y in terms of x, and we just divide by 2x minus 7. So therefore, y is equal to 1 over 2x minus 7 there. Okay? And that gives us the solution there to question 3. Moving on to question 4 here, we have a question that's split into two parts, A and B, taking a look at differentiation, and part C and D, taking a look at iteration. So starting with part A here first, we're asked to differentiate to find f prime of x. So we start with this function here, f of x, which is equal to 3e to the x minus a half of the natural logarithm of x minus 2. So to differentiate f of x here, we're just going to differentiate term by term. Well, starting off here, we've got 3e to the x. So if we differentiate e to the x, we just simply get e to the x. So we're just simply going to get 3 times the derivative here of e to the x. So we get 3e to the x. We've got minus a half of the natural logarithm of x here. So when we differentiate, so d by dx of the natural logarithm of x, this simply gives us 1 over x. So in that case, if we've got minus a half of 1 over x, then that's going to give us minus 1 over 2x. So just times in 1 over x by minus a half, we get minus 1 over 2x. And then finally, we've got this minus 2 here. So remember, when you differentiate a constant, that would just differentiate to give you 0. So when we differentiate here, this is simply what we get. So therefore, f prime of x is equal to 3e to the x minus 1 over 2x there. Okay, so that's part A there for the first 3 marks. Part B here, so we're told the curve with equation y equals f of x has a turning point at P. We know the x coordinate of P is alpha. And we want to show that alpha is equal to 1 over 6 e to the minus alpha. So how would we do this here? Well, the first thing to note is that if we're talking about a turning point here, that means f prime. So f prime, normally this would be f prime of x if the function was f of x, but we know the x coordinate of p is alpha. So we're going to say f prime of alpha here. F prime of alpha is equal to 0. Okay. And all we're going to do then is take our f prime of x here and just simply replace that with alpha. So that's 3e to the alpha minus 1 over 2 alpha. And we're going to set that equal to 0. So therefore what we've got here is 3e to the alpha minus 1 over 2 alpha. Okay, and we take this and set it equal to 0. So this is equal to 0. So the first thing to do here, or what makes more sense to me, is this minus 1 over 2 alpha. We just take that to the other side. So we add it to both sides here and balance the equation. So we get 3e to the alpha is equal to 1 over 2 alpha. Okay. And what we're looking to do here now is solve for alpha. Just like we've got here, that's what we're looking to show. So the first thing we can do is multiply both sides of this equation by 2. So that's going to give me 6e to the alpha is equal to 1 over alpha. Okay. And we're getting pretty close at this point here. Notice we've got 6e to the alpha. They've got 1 over 6e to the minus alpha. Okay. So we're getting there, but obviously we just need to do a bit more with this. And what we're looking for again is just alpha equals. So as this is 1 over alpha, I'm going to take the reciprocal of this side, but we also need to do the same to this side. So therefore, alpha is equal to 1 over 6e to the alpha. And just be slightly careful here. So 1 over 6e to the alpha is equivalent to this, but we just want to show that as well. So we know this e to the alpha here in the denominator, well, we can express that as 1 over 6 e to the minus alpha, okay, as required. And that gets our 2 marks there for part B. So now let's just clear the screen. So that was part A and B. Let's take a look now at part C and D surrounding iteration. And what we've been given here is the iterative formula, which is xn plus 1 is equal to 1 over 6 e to the minus xn. And we know the first term that we're going to use here, x0, is equal to 1. And what we're looking for here is the values of x1, x2, x3, and x4, giving the answers to 4 decimal places. So for x1 here, essentially when you're doing an iterative formula like this, or taking an iterative formula, and you're looking to find the next few values, we always use the previous value. So the previous value here to start with is this x0 equals 1. So we take that, and we plug it into this formula here. So that's going to be 1 over 6 e to this here. So that's going to be minus 1. And then once we get that value then for x1, for x2 we use that value of x1. So what would this look like here? So like we just said, it's going to be 1 over 6 e to the minus xn. So our xn here is this x0. So that's minus 1, like so. And if we put this into our calculator here, remember for the actual values of x1, x2, x3, x4, we only give them to 4 decimal places. So that's going to be 0.0613. However, now when we're calculating x2, we need to use as much accuracy as we can here. So we don't use the 4 decimal place that we've rounded it to. We're going to use as much accuracy as we can. Now in this case, this is what we got exactly. So 0.0613. So when we substitute that in for x2, this is going to be 1 over 6 e to the minus this. This is minus x1, so minus 0.0613. And if we evaluate this, what we get here is 0.1568 there. Okay, that gives us x2. Now for x3, like we just said, we use the previous value of x2. So that's going to be 1 over 6, so it's e to the minus of this value, but we want to use as much accuracy as we can. So what we got here is minus 0.156754 there. Okay, so notice we did round this to 0.1568, but when we then plug that into x3, we use as much accuracy as we can. And what we get here to 4 decimal places is 0.1425 there. Okay, and then finally we just want x4 here, so x4. Well, what would that be equal to? Well, again, this is going to be 1 over 6 e to the minus of x3 here. But again, we use as much accuracy as we can. That's minus 0.142485 there. Okay, and evaluating this on our calculator, what we get here is 0.1445 there. Okay, and that's all we needed there. We needed x1, x2, x3, and x4. It is worth pointing out here that you can use your calculator to save time doing iterative questions like this. So for example, what you'd do here is you'd enter this first value in, this 1, into your calculator and store that in the memory. And then what we'd do here is we'd do 1 over 6 e to the minus answer. And then when you press enter, that would give you your first value, that would give you x1. When you press enter again, you'd get x2, enter again, you'd get x3, and enter again, you'd get x4. So you can use your calculator just to speed it up, or just to double check your answer. It's always a nice checking tool. Okay, so that's part C there, only 2 marks, but not too much work. And finally for part D then, it says by considering the change of sign of f prime of x in a suitable interval, prove that alpha is equal to 0.1443, correct to 4 decimal places. In this case here, we need to determine the interval. So it makes sense here, if we're looking at this to 4 decimal places, that we split this into 2. So what I'm going to do here is I'm going to take f prime of 0.14425 and f prime of 0.14435. Okay, just so we can average this value here. And what we're hoping to show here is that one of these values will be positive and one will be negative. And if that's true, the change of sign indicates that the root lies in that interval. So I've already entered these into my calculator for f prime. I've cleared it off the screen already, but we had f prime here in part A. But just enter these values into your f prime. And what you should find here, so for f prime of 0.14425, you get minus 0.00069. And for f prime of 0.14435, you get 0.00206. Okay? And we can see clearly here then that this value here is negative, this value here is positive, so therefore the change of sign, indicates that the root lies in that interval there, and therefore alpha is equal to 0.1443 to 4 decimal places. So to 4 decimal places. I'm running out of room a little bit. We'll do it like that. Okay. And that gives us our solution there to question 4. Moving on to question 5 now, we have a question here dealing with trigonometry. So we're told the angle x and the angle y are such that tan x is equal to m and 4 tan y is equal to am plus 5, where m is a constant. We're also given that 16 sec squared x plus 16 sec squared y is equal to 537. And in part A, we're asked to find 2 possible values of m. And I think this question looks a little bit unusual and maybe a little bit complicated. But when you actually start applying the identities that you're familiar with, you'll start to find this question's not actually too bad. So let's start with the tan x equals m first. So what we're looking for here, and what we need to use, is the fact that 16 sec squared x plus 16 sec squared y is equal to 537. And we know that tan x is equal to m. So if we start with this tan x equals m, well, tan x is equal to m. Well, how can we relate this then to 16 sec squared x? Well, we know one of our trig identities here is that sec squared x, so sec squared x, is equal to 1 plus tan squared x. So if we have tan x equals m, in that case, tan squared of x will be this expression here on the left-hand side squared, and then we did square the right-hand side as well. So in that case, sec squared x is simply going to be equal to 1 plus tan squared x, like we just said. That will just be simply m squared. So for sec squared x, we get 1 plus m squared. So that's this part dealt with. Obviously, we need to multiply it by the 16 in a moment. But for now, we've got the sec squared x. Now let's consider the sec squared y. Well, we know 4 tan y, so 4 tan y is equal to am plus 5. So the first thing we need to do here is just get rid of this 4 on the left hand side. So we've just got it in terms of tan y. So we divide both sides by 4. So I get tan y is equal to am plus 5 all over 4. And again here now, all we need to do is make use of our identities. We already know what that identity is. In this case, we're looking for sec squared y. So in that case, sec squared y, that's going to be equal to 1 plus tan squared y. And we already know what tan y is. That's am plus 5 over 4. So in that case then, we're looking for sec squared y. So all we need to do is substitute in tan y squared. So sec squared y, that's equal to 1 plus this expression squared. So 1 plus am plus 5 all over 4 all squared. So clearly that would just be the numerator squared over the denominator squared. And if we simplify this expression here, what would we get? Well, we're going to get 1 plus, so it's going to be am plus 5 all squared. So that's just going to be a double bracket. So that's going to give us 64m squared. So you can actually write with the products here if you want, or if you're okay doing it off the top of your head, that's fine as well. So I get 64m squared. I'm going to get am times 5 and then another am times 5. So am times 5 is 40m. We need to double that, so we get 80m. And then finally 5 times 5 giving us plus 25. And this part here, these three terms are all over 4 squared. And 4 squared gives us 16. So we know sec squared y, so sec squared y is equal to 1 plus 64m squared plus 80m plus 25, with this part here all being over 16. So now we need to link it back to this expression here. Okay, we know 16 sec squared x plus 16 sec squared y is equal to 537. So using both of these then, so sec squared y and sec squared x, we just need to times both of them by 16 and set them equal to 537. So in that case we get 16 lots of sec squared x, which is 1 plus m squared, so 1 plus m squared, plus 16, so plus 16 lots of sec squared y, which is 1, plus this expression here, so 64m squared, plus 80m, plus 25, all over 16. And we know this here is equal to 537. Okay. So if I expand the left, or this left term here, this 16 times 1 plus m squared, well, I'm going to get 16 times 1 giving us 16, and 16 times m squared giving us plus 16m squared. So that's our first bracket dealt with. Dealing with the second bracket here, again, we've got 16 times 1 giving us another plus 16. So that's fine up to now. This part here, we've got 16 lots of this expression here. So as we're dividing by 16, if we times it by 16, they're just going to cancel. Okay, so they just cancel, and we just get left with the numerator here. So we get plus 64m squared plus 80m plus 25. And this is all equal to 537. Okay. At this point now, all we want to do here is just simplify the left-hand side. We're going to minus this right-hand side here and just set this as hopefully a quadratic that we can solve. So in that case then, I've got 16m squared plus 64m squared, so that would give me 80m squared. So I get 80m squared. We've just got the 80m here, there's no other m term, so it's just going to be plus 80m. And we've got 16 plus 25, and then we need to minus 537. So on our calculator, we're going to do 16 plus 25, and then minus 537, and that's going to be equal to 0. So in that case, we get minus 480, which is equal to 0. So hopefully I didn't confuse you when I said that. Obviously, 16 plus 25 minus 537, that's minus 480. But obviously, the right-hand side then is equal to 0. Okay, so that's what we mean there. And then at this point here, we're looking to solve this quadratic. It's up to you whether you try and divide here and simplify the quadratic, or just place this into your calculator and get your solutions. If you want to simplify this, you can divide each term by 80. So I get m squared plus m minus 6 is equal to 0. And from here now we can clearly see that this actually factorizes. What we get is we get m plus 3 and m minus 2. Okay, and that's equal to 0. And that gives us two possible values then of m. So therefore we get two solutions. We get m equals either minus 3, so m is equal to minus 3, or m is equal to my second solution here of 2. Okay, and that gives us our two possible values there of m, so either minus 3 or m equals 2. So that's part A done. So take a moment here just to kind of take notes here if you haven't done this question yet, and identify the solutions, because we will need now these two values for part B and C. So I'm just going to clear the screen here. So let's move on now to part B. And for part B, we're told that the angle x and the angle y are acute, and we're asked to find the exact value of sine x for part B, and for part C, cot y. So the important part here is that we're told angle x and angle y are acute. What that tells us is only one of these values of m will work. So remember, m we said was either minus 3 or m equals 2. And to identify this, you just need to do tan inverse here of one of these solutions. So for example, tan x is equal to m. So tan x is equal to either minus 3 or 2. And if you start with 2, I'm just going to start with the positive solution here. Then if you do tan inverse, so x is equal to tan inverse of 2, then this angle here that you evaluate is acute. It's less than 90 degrees. So we know straight away that m must be equal to 2. If you test it with m equals minus 3, you find that the angle isn't acute. Okay, so that's how we identify that m must be equal to 2. So that's important. Okay, so we know that m is 2. So for sine x then, so for sine x here, well, we know the trigonometric ratio here is the opposite over the hypotenuse. So that's the opposite over the hypotenuse. And I think it helps here if we just draw a right angle triangle. Okay, so if we draw a right angle triangle like so. Okay, mine's not perfect, but you get the idea. So it's a right angle triangle because we're doing trigonometry. And this is my angle here, x. And we said that tan x here, so tan x is equal to 2, because we said m must be 2. So tan x is equal to 2. So just applying a basic triangle here, with this base length here being 1, and this length here, the opposite length must be 2. Okay. In that case then, the hypotenuse is going to be simply a squared plus b squared, so 1 squared plus 2 squared, and then we take the square root of that, so that's going to be 4 plus 1, and we take the square root of that, so that's the square root of 5. And we can see here that this is true as well here, so the trigonometric ratio for tan is the opposite over the adjacent, so O over A, and the opposite here is 2, and the adjacent is 1, so 2 over 1 gives us tan x equals 2. So all we need to do now is just identify the ratio here. So sine x is equal to opposite over hypotenuse. So in that case, our exact value here for sine x is simply going to be opposite, which is 2, over the hypotenuse, which is the square root of 5. Okay, and that gives us our solution there for sine x, or our exact value for sine x. And for part C then, we want to identify the exact value of cot y. So for cot y then, we're working with this angle here. So angle y is such that 4 tan y is equal to am plus 5. Well, we know cot y is simply 1 over tan y. Okay, and we know what tan y is. So tan y is am plus 5 all over 4. So am plus 5 all over 4. And we also know what m is. We know that m is 2. Again, this is acute, so m must be 2 again here. So in that case, we've got 1 over tan y, so this is going to be 1 over am plus 5. So it's going to be 1 over 8 lots of m, which is 2, plus the 5, and this is all divided by 4. Okay. All I need to do now is evaluate this on my calculator, I get my solution, and that's my exact value for cot y. So this gives us 1 over, so 8 times 2 is 16, plus the 5 gives us 21. So this is 1 over 21 over 4. And in this case now, when you're doing 1 divided by something like this, well, this is just basic division of a fraction here, but the quick shortcut is that the 4 here will be times by the numerator. So it's going to be 1 times 4 is my numerator, giving me 4. and my denominator stays as whatever this is, so it's going to be 21. So that gives us 4 over 21 there. So cot y, the exact value is 4 over 21. And that gives us the solution there to question 5. Question 6 here is a question dealing with an arithmetic sequence. So we're told the second, third and fourth terms of an arithmetic sequence are 2k, 5k minus 10 and 7k minus 14 respectively, where k is just a constant. We're asked to show that the sum of the first n terms of the sequence is a square number. And in the top right here, you will also see just this little formula that I've included from your formula book, which we might find helpful towards the end of this question. So let's start with this question 6 here. And let's start with the first bit of information that we've been given. So we're told the second, third and fourth terms here of an arithmetic sequence are these three algebraic terms. So if I represent that then, my second term, u2, that is 2k. My third term, u3, that's 5k minus 10. And finally my fourth term here, 7k minus 14, so that's u4, that's 7k minus 14. So let's just pick a really basic arithmetic sequence here just to see what's happening. So if I pick my second term u2 as say 3, my third term here as 6, and my fourth term here u4 as 9, this would be an arithmetic sequence here with a common difference of 3. And the reason you can see that is then because u3 minus u2, so 6 minus 3 gives us 3, that must be equal to u4 minus u3, so 9 minus 6, and again that gives us 3. So in that case these must be equal, and we can say that is true with our algebraic terms here. So u3 minus u2 must be equal to u4 minus u3. Okay, so let's work this out then. So u3, that's 5k minus 10, 5k minus 10 minus u2, which is 2k, so minus 2k. Okay, so that's this left hand side here. Let's start by calculating the right hand side now as well. So u4 is 7k minus 14, so 7k minus 14 minus u3, so I'm going to put this all in a bracket just so we don't lose any minuses here. So that's 5k minus 10. Okay, the left hand side simplifies quite nicely. 5k minus 2k gives us 3k, so that's 3k minus 10 on the left hand side. For the right hand side here then, I've got 7k minus 5k, so that would give me 2k. And then we have minus 14 minus 10. So that's just why we're being a little bit cautious here with the bracket. So in that case, minus 14 minus 10 is the same as minus 14 plus 10. So that gives us minus 4. So we know that 3k minus 10 is equal to 2k minus 4. And from here now, we can actually just go on to solve k. So in that case, I'm going to subtract 2k off both sides. So I get k minus 10 is equal to minus 4. And then clearly add 10 to both sides to give me k equals 6. So we actually know what k is equal to now. All we need now is our first term, a, and we also need the common difference. So let's start with the first term here. So remember, be very, very careful. A common mistake here is to assume this is the first term and do two lots of 6, giving us 12 as the first term. Be very careful. Remember, this is the second term. So if we want the first term, that's just what comes before this, and we need to minus the common difference. So we also need to work out the common difference, and we actually need the common difference first here. So in that case, how do we work out the common difference? Well, the common difference then we can clearly see, if we just take a look at what we did here, u3 minus u2, that was simply 3k minus 10. So 3k minus 10, this represents the common difference, d. So that's 3 lots of 18, 3 lots of 6, which gives us 18. So 3 times 6 giving us 18, and we minus 10. So 18 minus 10, giving us 8 there for the common difference. And you could have also done that using the second part here, 2k minus 4. 2 lots of 6 is 12, minus 4 also gives you 8. So you could have done it with that expression there as well. So that gives us the common difference. We now want the first term a. And to work out a, we just need to take our second term here, which is 2 lots of k, so that's 12. And now we minus the common difference. So 12 minus 8, giving us 4 there. So we now have everything we need to find or show that the sum of the first n terms of the sequence is a square number. All we need to do now is apply this formula. Now the sum of the first n terms, we can express that in two different ways. We have this first part here, which is a half n times a plus l. Now we don't know the last term here, so that means we need to use this formula here. So therefore, we're a little bit messy here. Let's try it over here. In fact, I'm going to do it in a different pen color just to make it clear. Let's do it in red. So Sm, that's going to be n over 2, a half n, so n over 2, times 2a, so 2 lots of 4, so that gives us a there, plus n minus 1, we don't know how many terms it is, just the first n terms, so n minus 1 times by d, and we know d is equal to 8. Okay. And at this point here now, it's just a matter of simplifying and evaluating this. So let's start with this part here. So I've got n over 2 times 8, so that's a n over 2, giving us 4n. Okay, and this is the sum of the first n terms. I've now got n minus 1 times 8, so this will be plus n over 2 times an. 8 times n gives us an, and minus 1 times 8 giving us minus 8 there. Okay, now we evaluate each one here separately. Well, the first term here doesn't change. I've got 4n. We've got n over 2 times an, so that gives me an squared over 2, so that's 4n squared. And then finally, we've got n over 2 times minus 8, that gives me minus an over 2, which is minus 4n. Okay? So we've simplified it here. This is the sum of the first n terms, but we need to show that this is a square number. Well, we can see clearly this 4n cancels with this minus 4n, and I get left here with 4n squared. So how is this a square number? Well, in that case, we can simply express this as being equal to 2n all squared. Okay, and that is just clearly a square number. So this is a square number. So clearly a square number. So clearly a square number as required. Okay. And that's all we need to say there, really. It just shows that the sum of the first n terms of the sequence is a square number. Okay, so that gives us the solution there to question 6. Moving on to question 7 here, we have quite a short question, but hopefully some nice, easy marks to pick up. So what we've got here is a sketch of part of the curve with equation y equals f of x, which we can see here in figure 3. We're told the curve crosses the y-axis at the point 0, 8. We know the line with equation y equals 10 is the only asymptote to the curve. We also know we have a single turning point here, which is a minimum point. So for part A, we're asked to state the coordinates of the minimum point of the curve with equation y equals f of 1 over 4x. So how would we do something like this? Well, the clue is about understanding how these transformations work. So because this is just on the inside here with the x, this only affects the x coordinate. So the y coordinate will stay the same. So straight away, we give our coordinates here, the y coordinate won't change. So that's going to be a 5 no matter what. The x coordinate is clearly going to change though, because we've got this 1 over 4 here dealing with the x. So here, when you've got this number on the inside here, we divide by this value. So because this is 1 over 4, we're going to divide by 1 over 4. Which is essentially just the same as timesing by 4. So what I've got here now is 2 for my x-coordinate. That's the minimum point. So I'm going to do 2 divided by 1 over 4, which is the same as timesing by 4. So I get 2 times 4, which gives us 8. So I get 8, 5 there for my new minimum point there. That's with the equation y equals f of 1 over 4x. Okay. For part B, again, this is another question dealing with these transformations. We're asked to state the equation of the asymptote to the curve with equation y equals f of x minus 3. And again here, because nothing's happening to this x coordinate now, that will stay the same. So we know straight away all the x coordinates here, would stay as they are. The only thing that's going to be affected here now is the y coordinate. So we've got 3 y coordinates here, or 2 y coordinates, And we've got this equation here, y equals 10 for the asymptote. Now, obviously, we're only concerned about the asymptote, but we will discuss the other points as well, just to make it clear. So this is y equals f of x minus 3. And essentially, this is just a shift downwards now of 3 units. So if you think about it, this 0,8 would become, really it should be there, matching with that one, so it should be 0,5. So that would be 0,5. This 2,5 here, well, the 5, we'd go down 3 units, so 5 minus 3, giving us 2. So it would be 2, 2 there. And now the one that we're bothered about, this y equals 10, we're going to subtract 3 from it. So our new asymptote would be y equals 7 there. Okay, so that's how we get the equation of the asymptote to the curve with equation y equals f of x minus 3. So we get y equals 7 there. And now for part C, I think this is really the only part here which might cause some issues for this question. You have to think about it a little bit. We've got the curve with equation y equals f of x, which meets the line with equation y equals k, where k is a constant. And it meets it at 2 distinct points. So for example, if you think about drawing a line, so if I just do a line in a different colour, what it's saying is if you draw a line through here, it touches at 2 different points. So for example, here and here, for example, it touches y equals f of x at 2 different points. But it's asking for what is the equation here of y equals k. So we notice for y equals 10, it only touches, it's the asymptote at y equals 10. And for example, if y equals 5, so if we pick y equals 5, then that's going to be cutting through here, just the ones there like that. Okay. So essentially what we're looking for now is how do we determine this set of possible values for k? Well, if we think about it, it must definitely be less than 10. If y equals 10 is an asymptote, then y equals f of x keeps getting closer and closer to the asymptote, but it never actually touches it. Okay, so it keeps getting closer and closer to y equals 10, but never touches it. So it must be strictly less than 10, because y equals 10 is an asymptote, but it must also be greater than 5, because 5 here, it only touches it once there at that point. There's no other point where it touches y equals f of x. So in that case then, we give our solution for part C as strictly greater than 5 and strictly less than 10 there. So k is between 5 and 10, but not including those values. Okay, so that's how we get our answer there for part C, and that gives us the solution there to question 7. Taking a look at question 8 now, we've got a question here which is actually to do with quadratic modelling. And what we've been given is figure 1, which is a graph showing the trajectory of a rugby ball. The height of the ball above the ground h meters has been plotted against the horizontal distance x meters measured from the point where the ball was kicked. We're told the ball travels in a vertical plane and the ball reaches a maximum height of 12 meters and hits the ground at a point 40 meters from where it was kicked. For part A, we're asked to find a quadratic equation linking h with x that models this situation. And to start here, I think this can be a bit tricky if you've not really tackled questions like this before, but the first place we're going to start with is to remember that a general quadratic always has the same form. So it's ax squared, so ax squared plus bx plus c. And that's what we're looking for here. So we're linking h here with this quadratic equation. And this is just at the moment a general quadratic, but what we're going to do is use the information that we've been given here, such as the ball reaches a maximum height of 12 meters and it hits the ground at a point 40 meters from where it was kicked. We can use this information then to form our quadratic. So the first thing we can note here is when x is 0, so when the ball hasn't been kicked, well, the height is also 0. So this is 0, 0. And what we can say then is x equals 0, or when x equals 0, h is also equal to 0. Okay? And with that in mind, essentially here, if we think about it, 0 squared times by a, well, that'll just be 0. Anything times by 0 is clearly 0. Plus bx, so if x is 0, that will be 0. So what I get left with then on the right-hand side of this equation is c, but we also know h is equal to 0. So what that tells us then is that c is also equal to 0. Okay? So the first thing we found there is c, which we know is just equal to 0. We also know that when x is 40, so we're saying at this point here, 40 the height is 0. So when x is 40, we're saying that h is equal to 0. And what we can do then is we can form an equation. By substituting 40 into this equation here, where c is equal to 0, we get 40 squared times by a. So the left-hand side is 0 because h is 0, is equal to a lots of 40 squared plus b lots of 40, and then plus 0. Okay, c we know is 0. So in that case then we get 1600a, so 1600a plus 40b is equal to 0. And from here what we can do is we can rearrange for one of the variables. In this case I'm going to rearrange for b, make b the subject here. So in that case I get 40b is equal to minus 1600a, and therefore b is equal to minus 1600 divided by 40, which gives me minus 40a there. Okay. What we can also see from the graph and the information that we've been given here is that the ball reaches a maximum height of 12 meters, which if we look at the figure 1 here, the graph, we can see this must be roughly this point here. This is our maximum point. And if we link this to the x-axis here, we're told this has a maximum height of 12. So if we go across here, it's going to be roughly there. So that's 12. But where does this occur on the x-axis? Well, this is a quadratic, and due to the symmetry of this quadratic here, if we're going 40 units across, then this must be halfway. So that must be 20 there. Okay, so what we can also say is when x equals 20, so when x equals 20, we know the height is 12. Okay, and again what we can do then is substitute these into this quadratic here, and we can obtain another equation. So therefore 12, so that's h, so h is equal to a lots of 20 squared plus b lots of x, so that's 20 again. Okay, and again it's plus c, but c is equal to 0. So what would I get here? Well, I'm going to get 400a, so 400a plus 20b is equal to 12. And because we know that b is equal to minus 40a, we can simply go on to just substitute either into this equation here, or you can rearrange and make, in fact let's just substitute it, I think that's easier. So 400a plus 20 lots of minus 40a is equal to 12. Okay, so I'm going to get 400a minus 800a, so that's 400a minus 800a, and that's equal to 12. And unfortunately, we're running out of room a little bit, so take note of this line here. We'll clear all this, but carry on from here. Clearing all of that. So where we was up to was 400a minus 800a is equal to 12. So this would give me minus 400a. So minus 400a equals 12. And therefore, dividing through by minus 400, we get a. So a is equal to 12 over minus 400, which in this case will give me minus 3 over 100. Okay. And then finally, we can work out b, because we know b is equal to minus 40a. So in that case, if we just substitute in minus 3 over 100, then b is equal to minus 40 times minus 3 over 100. And what would we get here? Well, minus 40 times minus 3 over 100, that's just simply going to give me 120 over 100, which is 1.2 there. Okay. So we put all that back together now to give us our general quadratic. So what we said is h equals ax squared plus bx plus c. Well, we know c is equal to 0. We know a is minus 3 over 100. So I'm losing my voice a little bit. Hopefully we'll make it through the rest of this question. So I get h equals minus 3 over 100 minus 3 over 100 x squared plus bx, where b is 1.2, so plus 1.2x there. And again, you could express this as minus 0.03, so h is equal to minus 0.03 x squared plus 1.2x there. I think that looks a little bit neater given it in that form. Okay, So that gets us the first 3 marks there for part A. So again, we're going to have to clear all this. This question is quite large. But make sure you've got this quadratic equation written down here. We will need it for part B. So for part B, we're told the ball passes over the horizontal bar of a set of rugby posts that is perpendicular to the path of the ball. The bar is 3 meters above the ground. So the clue here in this question is the fact that we're told the bar is 3 meters above the ground. So what that's telling us then is the height, h, is equal to 3. So we know h equals 3. So all I'm going to do here now is set my quadratic, so minus 0.03 x squared plus 1.2x equal to what the value of h we've said here is, so that's 3. Okay. And all I need to do now is go on to solve this quadratic for x. Okay, so what would I get here? So we can write that as minus 3 over 100 x squared plus 1.2x equals 3. So in that case, I'm going to times everything through by 100. So it's going to give me minus 3x squared plus 120x is equal to 300. And then what I want to do is make this this quadratic x squared if we can. In this case, we can just divide through by minus 3 here. So I'm going to get x squared. I get x squared. I'm going to get minus 40x. And then finally, I'm going to get minus 100 here. But if I take it across the other side, that would become positive. So it's plus 100 equals 0. Okay. So all I've done here, just to make it clear, we've divided through by minus 3. Do the same here, divided by minus 3. Okay. And what I've got now is just a general quadratic. Whenever we see a quadratic that we're looking to solve, the first thing we should always do is check if it factorizes. And what we find for this one is it doesn't actually factorize. So there's 2 ways of tackling this now. We either use the quadratic formula or we complete the square. Now, I think this is easy enough through just completing the square. So we're going to halve this term here. So I'm going to get x minus 20. We square all of this. And what we do is we take the square of this term here. So minus 20 squared would be positive 400, but we take the negative of that, so I get minus 400. And then we also add 100. Okay, and this is equal to 0. And if we simplify this here, I get x minus 20 all squared. Minus 400 plus 100 is minus 300. And this is equal to 0. And from here now, we're just looking to solve for x here. And what you're going to see here, essentially, is we're going to get 2 values for x. So we're going to have to decide in a moment which value we omit. But let's get to that point first. So I'm going to take the 300 onto the other side. So I get x minus 20 all squared is equal to 300. Now we can take the square root of both sides. And this is where we get the 2 solutions from. So I get x minus 20 on the left-hand side. If we take the square root of this squared term, I just get x minus 20. And this is equal to plus or minus the square root of 300. So therefore, to get x equals, we just add 20 to both sides. So x is equal to 20 plus or minus the square root of 300. And clearly this is where we get the 2 solutions now. So x is either equal to 20 minus the square root of 300, or x is equal to 20 plus the square root of 300. Now, because we're looking for the greatest horizontal distance of the bar from O, then clearly this would be the plus solution. So x is going to be equal to 20 plus the square root of 300 there. Okay. And what we want to do is just give this in meters if we can. And that's a decimal value. So what I get here, if I put this into my calculator, is I get 37.3 meters there. Okay. So that gives us our solution there to part B. And I'll just give the answer to part C over here. So there's quite a few different things you can say as for a limitation of this model. But I think the most obvious answer here is there doesn't seem to be any wind or air resistance to this model. So we can just say there's no wind / air resistance. And something as easy as that gets us our mark there. Okay, but like I said, there's a few different answers you could give. Feel free to comment them down below if you want, or share any ideas down below. but I think that's the most obvious one there to put for 8c there for our limitation of the model. So that gives us our solution there to question 8. Moving on to question 9 now, we have a question here dealing with proof. And question 9 is split into two parts here. Part 1, we're asked to use proof by exhaustion to show this is true. And part 2 here, we're given that m cubed plus 5 is odd, and we need to use proof by contradiction to show that using algebra, m must be even. So let's start with the first part here. Now the first part is a proof by exhaustion, and remember, for proof by exhaustion, the clue's kind of in the name, we need to exhaust all possible cases. And the number of cases is given in the question here. So what we're told is that for n being a natural number here, but natural numbers less than or equal to 4, we need to show that n plus 1 cubed is greater than 3 to the n. So what we need to do now is consider the 4 possible cases. So that's going to be n equals 1, n equals 2, n equals 3, and n equals 4. There's a bit of a debate of whether you include n equals 0 for natural numbers. In this case, if you actually try n equals 0, it won't hold. So they're using the definition here that the natural numbers begin at 1 rather than 0. Okay, so we do from n equals 1 up to n equals 4. So I'll do n equals 1, n equals 2, n equals 3, and n equals 4 here. Okay, and we need to exhaust these 4 possible cases. So when n equals 1, the left hand side here of this inequality, that's going to be 1 plus 1, which is 2. So I do 2 cubed, which is equal to 8. And on the right hand side here of this inequality, I get 3 to the 1. So I get 3 to the 1, which is equal to 3. So therefore, 8 is greater than 3, which is true. That's what we wanted to show. So we've shown it's true for n equals 1. Now let's show it for n equals 2. And again, we just keep repeating this. So that's going to be 2 plus 1, giving me 3 cubed, which is 27. And now we do 3 to the power of n, which is 2 in this case. N equals 2, so I do 3 squared, which is equal to 9. And clearly again, 27 is greater than 9. Okay, so it's also true for n equals 2. And we just need to repeat this 2 more times now for n equals 3 and n equals 4. So we can see the pattern that's forming here. This will be 4 to the power of 3, and 4 cubed is 64. For the right hand side here, this is going to be 3 to the power of 3, so 3 cubed, and we know that's 27. And again, this is true for n equals 3 because 64 is greater than 27. And finally, let's just show this is true for n equals 4. So what I've got here is 5 to the power of 3, which is 5 cubed, giving us 125. And I've got 3 to the power of 4 here, which is 81. And again, one more time, we show this is true because 125 is greater than 81. And what we want to do here is we want to just give a conclusion essentially to this proof here. So what we say then is for n being less than or equal to 4, where n belongs to the natural numbers, then n plus 1 all cubed is strictly greater than 3 to the n, which is essentially what we just wanted to show, right? For n being a natural number where n is less than or equal to 4, then this holds. And that's exactly what we've shown here above, proving it for all 4 cases. So n equals 1, n equals 2, n equals 3, and finally n equals 4. So that gets us our first 2 marks there. That's always the issue with proof by exhaustion. It's a lot of work for not usually too many marks, but nothing too crazy mathematically. Okay, so that's the first part done. Let's take a look at the second part here. So we clear all this. So we're given that m cubed plus 5 is odd. So second part here, m cubed plus 5 is odd. Now we're given that, so we can't change that at all, because with a proof by contradiction, we want to assume something at the beginning. So we can't assume anything to do with this because we're given that m cubed plus 5 is odd. So we can't change that. But we need to use proof by contradiction to show, using algebra, that m is even. So it makes sense here to assume that m is odd. So we assume m is odd, or you can say not even. We can assume m is odd. Because what we said here is we need to show, using proof by contradiction, that using algebra, m is even. So if we assume m is odd, and we begin the proof like this, we should hopefully arrive at a contradiction towards the end of this proof. So if m is odd, then we can define m as being equal to 2p. It's up to you whether you do plus 1 or minus 1. I'll just put this as plus or minus 1. Okay, doesn't matter if you do plus 1 or minus 1, but just for clarity here, you can have either case. So what we're saying then is m cubed plus 5. So m cubed plus 5 is odd. But we know m is equal to 2p plus or minus 1. I'm going to take it as plus 1 here. So this is equal to 2p plus 1 all cubed. That's m cubed there. And then we need to add 5. Okay. So what I need to do now is expand these triple brackets here, this product of 3 brackets. It's up to you whether you use binomial expansion or you just do it by hand. I've already done the work to expand this. So what you will get here is 8p cubed. You'll get 12p squared. You'll get 6p. And then finally you'll get plus 1. And then we add another 5 to give us plus 6 there. Okay. So how do we arrive at a contradiction here? Well, it makes sense then to show that this must be even. If we're saying m cubed plus 5 is odd, if we can show this is actually even, then that's a contradiction because we're given that m cubed plus 5 is odd. Okay, so if we can show this is even, then clearly this is a contradiction to our original assumption, and in which case it must mean that m must be even. So to show this is even, I could just factor out a 2 and show that it belongs in the 2 times table essentially. Anything in the 2 times table must be even. So factoring a 2 out here, I get 2 lots of 4p cubed. So I get 4p cubed. I get 6p squared. 2 lots of 3p here, so 3p, and finally plus 3. Okay, and clearly now this is even. So this is clearly even. So we say this is clearly even, which is a contradiction to our original assumption. So there's a contradiction to our original assumption. And therefore, what we can say here, we just finish that up here, if m cubed plus 5 is odd, like we're given there at the beginning of the question, then m must be even. It doesn't work if m is odd. So if m cubed plus 5 is odd, then m must be even. Okay, and that's essentially the proof there complete. So we always need to give a conclusion again, just like we did with the first part here, and I think it's true for any proof question really. It's always nice to give a conclusion and basically just tell the examiner what we've shown there. So in that case, because we got 2 lots of this expression here, which was an even number, that's a contradiction to our original assumption, because we said m cubed plus 5 must be odd. Okay, but clearly we got an even number. And in that case then, if m cubed plus 5 is odd, then m must be even. Okay, so that gives us the solution there to the second part and to question 9 overall. Moving on to question 10 here, we have a question dealing with integration. And question 10 is split into 3 parts here. So we have the first part, which is where we're asked to find the integral of x sine x dx. And then the second part here, where we're asked to use the substitution x equals sec theta to show that this integral can be written as such. And then part B, we're asked to find the exact value of that integral. And underneath here, you'll see part of the formula book that we will find helpful for this question. So let's just start here with the first part. And with any integration question, it's always important to recognize what type of integration we need to do. So for the first part here, part 1, we're asked to integrate x sine x, okay, with respect to x. So the question is here, is this just a straightforward integration? Do we need to use integration by parts? Do we need to use substitution? That's what we need to identify here. And by looking at this integral here, as this is written as the product of 2 functions, this is x, this is sine x, then that means we need to use integration by parts. It won't be substitution, and a kind of a clue that we won't need substitution is the fact that we're using it in the second part here as well. It's very rare that we'd use it in this part and then be asked to do it again, so we need to use integration by parts here. And the integration by parts formula is given in the formula book. That's this formula here at the bottom. Okay. So in that case then, all we need to do is we need to take a look at our integral here and decide what we're going to assign it as u and what we're going to assign as dv by dx. And here, looking at these two functions, these two separate functions, it makes sense to pick u as x, because when we differentiate u, we just get 1, which makes the further calculation that we need really easy. So in that case, we're going to pick, we'll do it underneath, we'll pick u as x, and we'll pick dv by dx as the other function, which in this case is just the sine x. So that's equal to sine x. So what we need to do here is we need to differentiate u with respect to x. So that's going to give us du by dx. And obviously if you differentiate x with respect to x, that just gives you 1 there. Okay. And now we need to find v. So to find v, we integrate dv by dx with respect to x. And in that case, if we integrate sine x with respect to x, that just simply gives us minus cos x. Okay, so that gives us minus cos x. So what we've got here now is everything we need. All we need to do now is just apply the formula. So what we're saying here is the integral of u dv by dx with respect to x, which is what we're doing here. Well, that's equal to uv. So that's going to be u times v. So that's x times minus cos x. So what we get here is minus x cos x. So that's the uv part done. Now it's minus the integral. So it's minus the integral of v du by dx. So that's v, which is minus cos x, times du by dx, which is 1. And there's a bit of a trick here. You don't have to do it. You can keep the minus on the inside of this integral. But because this is minus cos x, that's just essentially minus 1 lot of cos x. We can apply linearity here. And we can take that minus 1 outside of the integral. And because it's already a minus, that's minus the integral. So that becomes a plus. Okay, so we add this integral here. And it's going to be cos x times by 1. So that's just cos x. Okay, and we're doing that with respect to x. So to finish here, all we need to do now is integrate cos x with respect to x, and we can't forget our constant of integration. We still need to apply that because we have no limits on the integral. So we're going to get minus x cos x, that won't change. And if we integrate cos x with respect to x, that just simply gives us sine x. So we get positive sine x. Okay. And don't forget the constant of integration there, so plus c. So that gets us the first 3 marks there. So that's part 1 done. Let's take a look at part 2a now. We're asking you to substitution x equals sec theta. So let's just clear all this because we're going to need quite a bit of room for this. And this is quite a lengthy question, especially given that this is only 3 marks, which is the same as the first part here. But there's definitely a lot more work to it. So we're using the substitution x equals sec theta. So x equals sec theta. Now, whenever we're using a substitution here, the first thing we should always do is differentiate this here. So we've got x equals sec theta, so we need to find dx by d theta. So we're looking for dx by d theta. And if we differentiate sec theta with respect to theta here, that just simply gives us sec theta tan theta. And this is a pretty standard result. You can write that as 1 over cos theta and differentiate using the quotient rule if you don't know how to show this result. But it is something that you should just be familiar with. So that gives you sec theta tan theta. So now we've got dx by d theta. What we need to do now is find our new limits, because if you notice here, our original limits are 1 and 2, but in the new integral that we've got here, it's 0 and pi over 3. So we need the new limits. So the new limits that we need to find, how do we get those? Well, what we're doing here is we're taking x equals 1 and x equals 2. So we've got x equals sec theta. So what we're saying then is when x equals 1. So when x equals 1, what we've got then is sec theta is equal to 1. And what we need here is the value of theta. That gives us our new limits. So how do we solve this trig equation here and get theta? Well, this is pretty straightforward. The actual answer here is simply going to be 0 for theta. But if you don't know how to show that, think about what sec theta actually is. Sec theta is 1 over cos theta. So what we've got here is 1 over cos theta is equal to 1. We'd now multiply both sides of this equation by cos theta. So I get cos theta is equal to 1. And then clearly if I want theta, I take the inverse or cosine inverse of both sides. So I get theta is equal to cos inverse of 1, which is simply 0. Okay, so that gives us what we can see here is our lower limit. That's a 0 here on this integral. So we've got our lower limit there. And now the second limit is going to come when x equals 2. So we need to show that as well. So when x equals 2. So when x equals 2 here, we say sec theta is equal to 2. And again, we just need to solve now for theta. And be very careful here. This isn't going to be theta is equal to cos inverse of 2. Be very, very careful here. What we're saying then is 1 over cos theta. 1 over cos theta is equal to 2. Multiplying both sides by cos theta, we get 2 cos theta is equal to 1. And now if we want cos theta, we divide by the 2. So cos theta is equal to a half. And cos theta is equal to a half. And therefore, if we wanted theta, so if we want theta, that's cos inverse of a half. Okay? And if you evaluate this on your calculator, what you find here is you get pi over 3. Okay? Your calculator might not give this in its exact form, which it'll give it as a decimal. And if that's the case, and you don't know how to get that into an exact form like this, then just take the upper limit here, pi over 3, and just put that into your calculator. Do pi divided by 3, and you should get the same value as what you got here. Okay? But that's how we've got our limits there. So what we found out is the correct limits. We've got pi over 3 is our upper limit here. That's what we've got. And we got 0 here as our lower limit. So that's the limits. That's kind of the first step there with the dx by d theta. And clearly we can rearrange this to be dx is equal to sec theta tan theta d theta, because we will need that in a moment when we substitute that in. Okay, so we've got everything we need now to kind of lay the foundations for this question. We're going to need to clear the screen because we've run out of room. It is quite a long question. So let's just clear the screen out and finish this. So we've got everything we need now. All we need to do is start applying the substitution here. So what we've got is the integral from 1 to 2 of the square root of 1 minus 1 over x squared. Okay, and this is with respect to x. Well, we know the new limits. We've shown that, so that's not a problem. All we need to do now is replace x here, this x squared, with x equals sec theta. Okay, so what I'm going to get then in this case is the integral. We know the new limits, that's 0 and pi over 3. And this is going to be the square root now. So this is the square root of 1 minus 1 over x squared. So if x is sec theta, then this is 1 over sec theta squared. So 1 over sec theta squared. Okay. And we need dx here. So like we said before, dx is simply going to be sec theta tan theta d theta. Okay. So now this looks quite complicated, and I don't think it's immediately obvious. So we need to do a bit of work here to get this into the correct form. When we're doing integration by substitution, we're always looking to see where we can start cancelling. And with this being a trig substitution like this, it's going to most likely use our identities that we are familiar with. The first thing we're going to do here is take this 1 over sec squared theta. So we know that 1 over sec squared theta, so 1 over sec squared theta, well, that is the same as 1 over, so we know sec squared theta is 1 over cos squared theta. So this is 1 over cos squared theta. And in that case then, this cos squared theta, we can times that by this 1 on top, and I'm going to get cos squared theta there. Okay, so this is the same as cos squared theta. Okay, so when we actually apply that here with this square root, 1 minus 1 over sec squared theta, this is going to be now, this 1 over sec squared theta is just cos squared theta. So what I've got here now is the integral from 0 to pi over 3 of the square root of 1 minus cos squared theta. 1 minus cos squared theta, and we've still got our sec theta, tan theta, d theta. So sec theta, tan theta, d theta. Okay, but at this point, this should look a lot more promising now. We've got the square root of 1 minus cos squared theta. And again, we need to use our identities here. So this 1 minus cos squared theta should look very familiar here, because we know that sine squared theta, so sine squared theta plus cos squared theta is equal to 1. So we can rearrange here by minusing the cos squared theta to get 1 minus cos squared theta. So sine squared theta is equivalent to 1 minus cos squared theta. And then if we just want to get the square root of 1 minus cos squared theta, we take the square root of both sides. So if we take the square root of this left-hand side, we just get sine theta. So sine theta, in this case, is just equal to the square root of 1 minus cos squared theta. Okay, like so. So what we can do then is replace this part here now with sine theta. So I've got the integral from 0 to pi over 3 of sine theta. So we know this part here now is just sine theta. So this is sine theta, sec theta, tan theta, d theta. So there's a lot of thetas here, but that's what we should have so far. And again, at this point now, at this place here, it's just a matter of simplifying. So what we notice here is that we should get tan squared theta d theta. And we're actually really close now. We've got tan theta here, we've got our d theta here. The only issue is this sine theta and sec theta. But remember, sec theta is 1 over cos theta. So what I've got here now is sine theta times 1 over cos theta. And we know that sine theta over cos theta gives us tan theta. Okay, and that's what we're looking for here. We're looking for tan theta times tan theta to give us tan squared theta. So in that case then we can simply write this as tan squared theta using this here, because this is 1 over cos theta. So I'll write it in full just so we can see where this is coming from. So that's sine theta 1 over cos theta tan theta d theta, and that's equal to what we want to show here. So from 0 to pi over 3, that's sine theta over cos theta giving us tan theta here. So I get tan squared theta d theta as required. Okay. And like you see, that is only 3 marks, just like we did in the first part. So I think the marks are a little bit, out of line from the second part to the first part, but hopefully it wasn't too bad. Okay, so that's the second part complete there. And then in part B, we're asked to find the exact value of this integral. So let's just clear all this, just so we can finish this question. And with part B here, even if you couldn't do the first 2 parts, you can still go on to answer part B. And the reason for that is because we know what this integral is equal to. So notice these integrals here are the exact same, but we know this integral can be expressed like this. So what we're looking for then is just to find the integral of tan squared theta d theta from 0 to pi over 3. Okay, that's all we're looking for here. Now, tan squared theta, we can't just integrate it like that. And you can almost see that from your formula book here. Notice we've got tan kx. We can integrate something of that form, but not tan squared. So in that case, we need to use our identities. And the identity we're going to use here is the fact that we can express tan squared theta as being equal to sec squared theta minus 1. Okay, so in that case then, we're not integrating tan squared theta here. We're going to replace that with sec squared theta minus 1, because that now we can integrate. Notice we've got sec squared here, so we can integrate this nice and easy. So what we're looking for here is the integral from 0 to pi over 3 of sec squared theta minus 1. I'll just put this all in a bracket just to make it clear. It's with respect to theta. Well, sec squared theta, using our formula book here, where k is just 1, that's going to be 1 over 1 tan k, which is 1 x, or in this case it'll be theta for us. So that's just going to simply give me here tan theta. That gives me tan theta. I get tan theta. If we integrate minus 1 here with respect to theta, that just gives me minus theta. And we can't forget our limits here of 0 and pi over 3. And clearly here, just to finish this question now, we just need to substitute our limits in. Remember, we start with the upper limit, so that's going to give me tan of pi over 3, so tan pi over 3, minus theta here, which is, again, pi over 3. If we substitute the lower limit in here, well, tan of 0 will just give us 0, and then minus 0 as well. So this lower limit here is just all equal to 0. So we don't need to do anything with the lower limit. All we need to do now is evaluate this and give it in its exact form. Well, tan of pi over 3 simply is root 3. So I get root 3 here minus pi over 3. Okay? And that's our answer there in its exact form, or given the exact value of this integral here. So that's the part B done there. And that gives us the solution to question 10. Moving on to question 11 now, we have a question here which is quite lengthy, to be honest, but it's mainly surrounding differentiation. So the first two parts are essentially setting up for part C and part D. So let's just start with part A here, and let's just take a look at the question first and just kind of decipher what we actually need to start with. So 11A. So what we're told here is in figure 4, this shows us the plan of a pool. And the shape of the pool consists of a rectangle joined to an equilateral triangle and a semicircle. Okay, so we've got our equilateral triangle, we've got our rectangle here, and then we've got our semicircle. So we're given a few lengths here, such as this length here, which is x, this length here, which is y, and we're told the area of the pool is 50 meters squared. So we know the area of this equilateral triangle plus the area of this rectangle plus the area of this semicircle must equal 50 meters squared. And then we're just simply asked to show that y equals 50 over x minus x over 8 bracket pi plus 2 root 3. And to start with, I think this probably looks a bit overwhelming. We've been given all this information here, and then we're just asked to show that this is, or asked to show that y equals this expression here. And it can be quite tricky to see how to start with these kind of questions, but what I'd recommend is to use the information that we've been given. So we know this length here is x, and this is an equilateral triangle, so clearly all lengths are x meters, so that's x meters, and this here will also be x meters. And because this length here of the rectangle is x meters, this also means that this length will be x meters. And once we put these lengths in to our shape here, we can actually go on now to work out the area of all three shapes. This is an equilateral triangle, so to work out the area, we simply just need to apply the formula for the area of a triangle. So the area of this, so A, is given by a half AB sine C. So we just need to apply that here for our equilateral triangle. And remember, this is an equilateral triangle, so all the angles will be 60 degrees. Okay? So we know that fact there. This is a rectangle, so it'd be really easy to work out the area of that. And then we'll also come to the semicircle in a moment. So let's just start with a triangle here. So area of triangle. So area of the triangle. How do we work that out? Well, in that case, like we just said, that's a half AB sine C. And it doesn't matter what you assign as A, B, and C here, because it's an equilateral triangle, all lengths and angles are equal. So in that case, then, all we simply need to do here is use the fact that this is a half. If we say this is A and this is B, then that's x times x, because it's AB, so we get x squared, so we get a half x squared sine 60 degrees there. Okay, because again, sine C, doesn't matter which angle we pick, they're all 60 degrees. And if we simplify this here, well, we know sine 60 is equal to root 3 over 2. So what I get then is root 3 over 2 times a half, so I get root 3 over 4, so root 3 over 4 x squared. Okay, so that's the first shape that we've got here. So we've done the triangle. The area of the rectangle is nice and straightforward, so area of rectangle. For the area of the rectangle, all we simply do here then is x times y, so that's going to give us xy, nothing else to that. Let's not overcomplicate things. And then finally, we just need the area of the semicircle, so area of semicircle. Okay, and how do we work out the area of the semicircle? Well, we know the area of a circle. A is pi r squared, So clearly, if we just want the area of a semicircle, we just divide that by 2. So that's going to be pi r squared divided by 2. Okay. Well, we know r. Well, we know the diameter here is x. So r, in this case, the radius is a half x, or x over 2. Okay. And what we're going to get then here is pi times the radius squared. So the radius is x over 2, so that's x over 2 squared. And then we divide all of this by 2. Okay. And if we just simplify this here, this is going to be x squared over 4 times by pi, and then we divide it by 2. So overall, what I get here is 1 over 8 pi x squared. Okay. So I get pi x squared there. And at this point here now, we've got everything we need to actually finish pi a. So we've got the area of the triangle, area of the rectangle, and area of the semicircle. Like we just said, we know the area of the pool is 50 meters squared. So to get the area then, we just add all these parts together. So I'm going to take root 3 over 4x squared plus xy and plus 1 over 8 pi x squared, and just add all of these together. So the area then is equal to root 3 over 4 x squared plus xy plus 1 over 8 pi x squared. And we know this is equal to 50. And from here now, it's just a matter of simplifying this until we get it equal to this expression. So where do we begin? Well, as this is y equals, the only y I actually have is this xy here. So it makes sense to take everything onto the other side, and then eventually we're just going to divide through by x. So therefore, xy is equal to 50 minus 1 over 8, so minus 1 over 8 pi x squared, and then minus root 3 over 4 x squared. And we're pretty close here now. We just want to start simplifying where we can. I've got this minus 1 over 8 pi x squared minus root 3 over 4 x squared. So notice I've got an x squared here in both of these, so we can factor that out. And I'm also going to factor the 1 over 8 out because we've got x over 8. So if I factor 1 over 8 x squared out, when we divide by the x in a moment, that's just going to leave us with minus x over 8, or minus 1 over 8 x. Okay? So I'm going to get xy is equal to 50 minus x squared over 8. So I'm going to get pi at the front of the bracket, so I get pi. And then here, so if you factor out 1 over 8 out here with the x squared, essentially what you're thinking about then is what do I times this minus x squared over 8 by to get minus root 3 over 4 x squared. Okay, so in that case we get plus 2 root 3. So I get plus 2 root 3. And then from here, we just divide both sides of this equation by x. Because we just want y equals, so therefore I just divide by x. And in that case then, when we divide both sides by x, I get the expression that we wanted. So therefore, by dividing by x, that gives us the expression we need. So y is equal to 50 over x. So I get 50 over x minus x over 8 pi plus 2 root 3 there. Okay? And that's part A done there. So like you see, it's a lot of work for 3 marks, but that's just what we've got to do. So that gets us the first 3 marks there. So that's part A done. Let's take a look at part B now. And part B is pretty similar. Again, we're just looking to show this expression here. So it's a hence question, so that means we need to use part A to help us. And even if you can't show part A, you can still go on to do part B. So part B here, it asks us to show that the perimeter, p meters of the pool, is given by this expression here. Now for the perimeter, so for the perimeter here, p, that's just going to be x plus y here. And then we just need this circumference here, or half of this circumference of what would be my circle. Okay, so because it's a semicircle, we're just going to take the circumference of a circle, divide it by 2. Okay, so that's going to be x plus x, so x plus x, like we just said, these two lengths. Then it's going to be y plus y, so plus y, and then finally this circumference here. So or the semi-circumference here. So how would we work that out? Well, for a circle, the circumference is equal to pi times the diameter, so pi d. So in that case, the circumference that we want here, we're just going to divide that by 2. Okay. We know the diameter here is x, so that's just simply going to be pi x over 2. Okay, so plus pi x over 2. And if we just simplify here, I get p equals 2x plus 2y plus pi x over 2. And what I can do then is factor out the x here. So what I get for p is 2y plus x lots of 2 plus pi over 2. Okay. You can just skip to this third line here from here if you find that easier, but just to make it clear what we've got, that's where we're up to at the moment. Now, we know what y is equal to. That was given to us in part A. So like I said, even if you couldn't show that, we still do have that expression, so we can go on to show this expression for part B as well. And all we're going to do is simply substitute y in now. So we've got p equals 2 lots of y. So y is 50 over x minus x over 8 times pi plus 2 root 3. So in that case, we get 2 lots of 50 over x. That's going to be 100 over x. So I get 100 over x. And this x over 8, if you times that by 2, that would be minus 2x over 8. So that would be minus x over 4. So minus x over 4. And then the bracket won't change here, if that makes sense. So I've got minus x over 4. And then I've got the bracket, so I get pi plus 2 root 3. So just so I don't confuse myself. And then don't forget we've got this x here as well. Okay, so I get x lots of 2 plus pi over 2. So just to make it clear, I had to confuse myself then. There's 2y, so that's 2 lots of this expression here. So I get 100 over x minus x over 4 pi plus 2 root 3. And then don't forget the x times 2 plus pi over 2. Okay, so that's the expression there for p. And from here now, we're on the right path. We just need to keep simplifying this until we get this expression here. So where do we begin? Well, if you're ever in doubt, what I'd do is just expand brackets. So p is equal to 100 over x. I get minus pi x over 4 or minus x over 4 pi. It's up to you how you express this. So minus x over 4 pi. And then I'm going to get minus, so this is minus x over 4 times 2 root 3. So when you times these together, the 2 will cancel with the 4 there and leave me a denominator of 2. So I'm going to get minus, root 3 over 2x. Okay. And then we move on to this bracket here. So I'm going to get plus 2x. So plus 2x. And then I'm going to get plus pi x, or plus x over 2 pi. Okay. Since I've done that as minus x over 4, I'll do this as x over 2 pi. Now, let's look at this expression here to see what we're aiming for. So we've got the 100 over x, that's fine. And what they do is they put that as plus x over 4, and clearly they've factored that x over 4 out at some point towards the end. Now, I've got this minus root 3 over 2 x, I've got the plus 2x here. We've also got this minus x over 4 pi and the plus x over 2 pi. So here, I think it makes sense to take this pi and simplify it, because what they've got here is just clearly pi x over 4. So that's what we want to show here. So I've got minus x over 4 pi plus x over 2 pi. And if we simplify that, then I get p equals 100 over x. So I get 100 over x minus x over 4 pi plus x over 2 pi. That does simplify to give us x over 4 pi. So x over 4 pi. And then we'll leave the other two parts here. So I've got plus 2x, and minus root 3 over 2x there. Okay, we're not going to touch them just yet. But from here now we can just show these two expressions are equivalent. So p is equal to 100 over x. We've got that already, 100 over x. And now we factor out the x over 4. So we factor out the x over 4. So I get plus x over 4. We've got the pi here, so that's great. X over 4, we factor that out, so that just leaves me with pi. Perfect. We've got the 2x. So if you factor out x over 4, what do I times x over 4 by to give me 2x? Well, that clearly must just be 8, because 8x over 4 gives you 2 8. So that's plus 8 And then finally, doing the same here, what do I times x over 4 by to get minus this minus root 3 over 2? Well, that must just simply be minus 2 root 3 there, because we factored the x over 4 out. So that just leaves me with minus 2 root 3, and we close the bracket there. Okay, so we factored out x over 4 there, and that's what we get left with. Okay, so that's the answer to part B. Another 3 marks, like you can see, a lot of work. It's very easy to trip up. But that's A and B done. So now we move on to the differentiation part. Moving on to part C here, I accidentally messed up the recording, so we're going back to it using calculus to find the minimum value of P. So if we're using calculus and we're finding a minimum value, then that tells us we need to differentiate. So we've got P equals here. So we've got P, and even if you couldn't actually show part A or part B, we can still go on to do part C and D because we have the expression for P. So I'm going to write this in index notation. So 100 over x. So 100 over x, remember that's the same as 100x to the minus 1. So this is 100x to the minus 1. And I've got plus x over 4 times by these constants. So each term here is a constant. So if I multiply it by x over 4, what I've got then is each constant divided by 4. So for example, pi over 4 times by x, a over 4 times by x. And when you actually go on to then differentiate those terms later, you will just get, for example, pi over 4, a over 4. Because they're all multiplied by x, the x will just become 0 when you differentiate. So what I'm going to do here then is write them all over 4, but keep the x on the outside, just so we can see what will happen later. So I get x lots of pi plus a minus 2 root 3 all over 4. Okay? And here now, we want to differentiate from here. So we've got p equals, we want p prime. So p prime is our first derivative. So that's going to give me minus 100. So the minus 1 comes out in front and we times it by the 100. So I get minus 100 x, and we subtract 1 from the power. So that gives me minus 2 plus, now as each of these terms are times by x, the x will essentially just give you one lot of whatever's here. So because it's pi plus 8 minus 2 root 3 over 4, I'm just going to get what's inside the bracket. So I get plus pi plus a minus 2 root 3, and that's all over 4. Okay? So that's the first derivative. Now, we don't need to actually do the second derivative here. Remember, we only need the first derivative to find the minimum value in this case, but we will need the second derivative for part D, so I will find it while we're here. So p prime prime. Well, this part here will just become 0. They're all constants when you differentiate them. They become 0. But this minus 100x to the minus 2, well, the minus 2 comes out in front and we times that by minus 100 to give me 200x to the minus 3 there. Okay? So we want the minimum value of p. So for the minimum value, here, remember that we set the first derivative, p prime, equal to 0. If you think of a really basic example of just a quadratic, for example, if we take our quadratic here, the minimum value, that occurs when the first derivative, the gradient, is equal to 0. Okay, so we set the first derivative equal to 0. And what we need to do then is take the first derivative, set it equal to 0, and solve for x. So what we've got is minus 100x to the minus 2 plus pi plus a minus 2 root 3 all over 4 is equal to 0. And I think the first step here, or the first step that makes the most sense, is to take this minus 100x to the minus 2 onto the other side. Make that positive. So I get 100x to the minus 2 is equal to pi plus a minus 2 root 3 all over 4. Okay, and this 100x to the minus 2, so 100x to the minus 2, just like we did here, that was 100 over x for 100x to the minus 1. So in that case, that would be 100 over x squared. Okay, so I get 100 over x squared is equal to this expression, pi plus a minus 2 root 3 all over 4. And we're looking to solve for x here. Now, don't overcomplicate this. I know it looks maybe a little bit tricky, but the first thing to do is essentially get this x squared to be the numerator. And when you've got two fractions like this that are equal, and they're both fractions, what I can do is flip this fraction here, so that would be x squared over 100, and then I need to flip the second fraction. So what I'm going to get then, if we do that up here, is I get x squared over 100 is equal to 4 over this expression here. So pi plus a minus 2 root 3 there. And therefore, if we want x squared, we just times everything through by 100. So that's going to be 400 over pi plus a minus 2 root 3. And then clearly, if we just want x, we take the square root here. Okay, so therefore, x is equal to the square root of this expression. So 400 divided by pi plus a minus 2 root 3. And then we just need to put this into our calculator here. And what we should find, and remember, we only take the positive solution here. X is a length, so we can't have a negative solution. X is equal to, and again, to three significant figures, that would give us 7.22. So we get 7.22. And what we need to actually find now is the minimum value. So we've got the length of x there, but we now need to find the minimum value of p. So therefore, to find the minimum value of p, we just substitute this value that we found for x here into p. Okay. So therefore, the minimum value, let's do it in a different pen colour. In fact, let's just clear the screen, and we'll do it in a different pen colour. So the minimum value is found then by, like we just said, subbing x equals 7.22 into p. So therefore, I get p is equal to 100 over x, so that's 100 over 7.22, plus x over 4, so that's 7.22 over 4, and then I get, we multiply that by pi plus a minus 2 root 3, and just put this into your calculator, and then give your answer to three significant figures here, and what you get is 27.7 there. Okay, and that's to three significant figures. So that's the solution to part C. And then finally for part D here, so for part D, we need to justify by further differentiation that the value of p that we found is a minimum. And to justify whether we found a minimum or a maximum, we need to use the second derivative. So we're going to use now the second derivative. So that's p prime prime. We found that earlier, but just so we've got it on the screen again, let's write that down. So p prime prime, that's 200x to the minus 3, or 200 over x cubed. Okay. Now we've said here that x is 7.22. So all I need to do is simply substitute that value of x into p prime prime here. So we get 200 divided by 7.22 all cubed. And if this is a minimum, this value here should be greater than 0. If it's less than 0, that would imply we have a maximum. And if we evaluate this on our calculator, what you should get is something around 0.531, so on and so on. Okay, depending on how you round this, but something close to this. So I get 0.531, which is greater than 0, and therefore that means that p is a minimum. So therefore p is a minimum because the second derivative is greater than 0. So that's all we need to do for part D to justify using further differentiation that the value of p we have found is a minimum. So that gives us the solution there to part D and the solution to question 11 overall. Moving on to question 12 now, we have a question here dealing with circles. So this is split into three parts here. We have A, B and C. So part A, pretty standard. We're given the equation for the circle. We're just asked to find the coordinates of the centre of the circle and the exact value of the radius. So this should hopefully be quite a standard, easy question to start with, or part to start with here. So 12A. So we've got the circle here, which is given by x minus 3 all squared plus y plus 4 all squared is equal to 30. And for a general circle, we use the equation x minus a all squared plus y minus b all squared, and this is equal to r squared. And for the centre of this general circle then, so for the centre here of our general circle, well, we take a look at the x minus a and the y minus b. And the centre is just the opposite to this sign. So if I've got x minus a, then the x coordinate of the centre would just be positive a, so that's a. And the y coordinate here is given with the y minus b, and again, it's just the opposite sign. So if that's minus b, that will be positive b there for the y coordinate. If that was y plus b, then it would be minus b. So in that case, we just take a look at this equation here for our circle. And for the centre then, so for the centre, we can see clearly, using this equation, that must be 3 minus 4. So the centre is equal to 3, because that's minus 3, we take the opposite, so that's positive 3. And for the y coordinate then, because it's plus 4, we say minus 4 there. Okay, so that's the coordinates for the centre of the C. And now we want the exact value of the radius of C. So how do we find the exact value of the radius? Well, we use our equation again. So the radius comes from this part here, this r squared. So what we're saying here is r squared is equal to this part here on the right hand side of this equation, so that's 30. So if we just want the radius then, the exact value of the radius, well, we take the square root of both sides. And clearly we only take the positive solution here because we can't have a negative length for the radius. Okay, so therefore r is equal to the square root of 30. Okay, and that gives us the exact value there of the radius of C. Now for part B, we are given that the point P with coordinate 6k, where k is a constant, lies inside the circle C. And what we want to do here is show that k squared plus 8k minus 5 is less than 0. And mathematically, part B isn't too tricky, but I think it might be a little bit, or it might be a bit tricky to see where we start and how we actually end up with this quadratic inequality here. Now, the clue here, well, we're given this coordinate here, or these coordinates 6k, and we're told that k is a constant which lies inside the circle C. So that's the important bit here, the fact that it lies inside the circle C. That's what essentially forms this quadratic inequality. Because if we think about this, as we're told that P lies inside the circle, then from the centre to P must be less than the centre to the radius. Okay, so if you think about this just by sketching just something rough like this here, so we do it down here. So if I say this is my circle, it doesn't have to be perfect. So we said the centre was 3 minus 4, so 3 across, down 4, so let's just say that's there. And I'm just going to draw something rough here just so we get an idea of what this looks like. So let's just say that's my circle, which is shocking. Let's say that's the centre there. Okay, so that's my circle. This might not be perfect, but let's just say that's the circle we're dealing with here, C. Now what we're saying is the point P, which has the coordinate 6k, so that's say 6 along here, and then we don't know the height, it's just k, so it can be any point along here. Okay, what we're saying is from the centre here to any point on this line is less than from the centre here to any point outside or on the circumference of the circle. So in that case then we can find the distance from the centre to the coordinates here 6k, and then we can set that as being less than the radius. Okay, we know the radius here is the square root of 30. So in that case then for B, what we say by finding the distance then is the square root of, so it's going to be 6 minus this value here, so 6 minus 3 all squared, plus, and then it's going to be k, so it's going to be k minus, so it's going to be minus 4, so that becomes plus 4 there. So we get k plus 4 squared. And we've just said there that this value here, because it lies inside the circle, must be less than the radius. Okay, if you think about the radius, that value from the centre to a point on the circumference is the square root of 30. So we know that any point here on this line must be less than the square root of 30. So we say that's less than the square root of 30. Okay, and from here now, this will eventually take us to this. Okay, so the first thing I'm going to do here, as we've got square roots on both sides, I'm going to square both sides. Okay, so if I square the left hand side here, I just get left with whatever's underneath the square root. So I get 6 minus 3 squared plus k plus 4 squared is less And again, square the right hand side here. So if you square root of 30, that just simply gives us 30. Okay. Well, 6 minus 3 gives us 3. So we get 3 squared there, which is 9. This is a double bracket here. So expanding this double bracket, so that's going to be k plus 4 times k plus 4. So clearly in that case then I'm going to get k squared. I'm going to get 4k and I'm going to get another 4k. So adding them together I get 8k. And then finally 4 times 4 gives me 16. Okay. We've also got on the right hand side here that this is less than 30. Now clearly this inequality here, this quadratic inequality, is less than 0. So the first thing I can do is subtract 30 off both sides. So what I've got here is 9 plus 16, which is 25, minus the 30. So 25 minus 30 gives me minus 5. And therefore what we end up with here is exactly what we wanted to show for part B. So what I get then is k squared plus 8k, and then 25 minus 30 giving me minus 5. And that's all less than 0. Okay, so that's as required for part B. Okay, so that gives us the solution there to part B. And then finally we arrive at part C here to question 12, where we're asked to hence find the exact set of values of k for which P lies inside C. So how do we do this? Well, part C is quite straightforward. It just boils down to solving that quadratic inequality. So we've got the inequality here. So even if you couldn't do part A or B, for example, you still could go on to answer part C by solving this quadratic inequality here. Okay, so just so we've got enough room, let's clear the screen. And then let's take a look at part C. So for part C here, we're just looking to solve this quadratic inequality. So k squared plus 8k at minus 5 is less than 0. And we should always just check to see if it factorizes. Unfortunately, in this case, this doesn't factorize. So we either need to solve it using the quadratic formula or by completing the square. Now, with this being a straightforward quadratic equation with the coefficient of here, of this k squared being 1, I'm just going to complete the square. So I'm going to get k plus 4. We square this term here, and we take the negative square here. So 4 squared would be 16, but we want minus 16, and we minus what's left over, so the minus 5 there. Okay, and we just set this equal to 0 for now. So simplifying this left-hand side here, I get k plus 4 squared minus the 21 is equal to 0. And from here now, we're just looking to solve for k. So therefore, adding 21 to both sides, I get k plus 4 all squared is equal to 21. Now taking the square root of the left-hand side and the right-hand side here, I get k plus 4 is equal, and be very careful here, we'll get both the positive and the negative solution here, so I get plus or minus the square root of 21. And then finally, to get k, we just subtract 4 off both sides, so therefore k is equal to minus 4 plus or minus the square root of 21. Okay? So what we've got here are essentially the critical values. We know now where this quadratic cuts through the x-axis, and if we just sketch this here again, just so we get an idea. And I would recommend this whenever you're solving a quadratic inequality, just so you can see what's actually happening. With our quadratic here, it'd cut through at minus 5, let's just say that's there. And it's going to cut through at minus 4 minus the square root of 21. And that would be, say, here. So that's minus 4 minus the square root of 21. And then we'll have this point here, which is the positive part there. So minus 4 plus the square root of 21. Okay. And then my quadratic is going to look something like this. Don't have to be perfect, just so we can see it. And I get that. Now what we're looking for here is where is this less than 0? And this is simply less than 0 between here. Okay, so between this point here and this point here. So again, just use a different pen colour just to highlight that. So we're looking between here. That's where this is less than 0. Now we just have to be slightly careful when you actually give the answer. Make sure to take note of the inequality that's being used for the quadratic inequality. So we know this is strictly less than 0. So when I give the solution, we need to make sure they are strictly less as well, or strict inequalities, I should say. So what I get then for k, it must be between -4 minus square root of 21. So it's going to be greater than this value and strictly greater, but strictly less than -4 plus the square root of 21. Okay. So again, make sure these inequalities are strict inequalities, and that comes back to the original quadratic inequality here that we were presented with in part B. But that gives us our solution there to part C and the solution to question 12 overall. And finally, we arrive at the last question here, question 13. And what we've got here is this summation from n equals 2 to positive infinity of 3/4 to the power of n, so 3/4 to the power of n times by cos 180 n degrees. Okay, and we want to show that this is equal to 9/28. Now, this topic here, it's not explicitly mentioned on paper 1. I decided to throw it in just a bit of extra practice and just to give us an extra question to finish with, but it's always good practice to do questions like this. So where do we begin with a question like this? So there's not too much given to, or telling us how to actually get to this result here. We're just given this summation and we're asked to show this. And if you're ever given a question like this where you're not really sure where to begin, you just kind of dropped a bit in the deep end here, then what I'd recommend is starting with the first few terms of this series. So if I say n equals 2, what would we get here? Well, the first term then is going to be 3/4 to the power of n, where n equals 2, so that's 3/4 squared, times cosine of 180 times n. So 180 times 2, giving us cos of 360 degrees. We don't need the brackets, I'll just get rid of it here. You can put them in if you want, but they're not really necessary in this case. So that gives us 360 degrees there. And if we evaluate this first term here, I'm going to get 3/4 squared, so that would be 9/16, and cos of 360 degrees is just equal to 1. So what I actually get for the first term here is 9/16, or you can leave it as 3/4 squared if you prefer. Okay, so the first term in this series is a, and that's equal to 9/16. And let's consider the next term here, so n equals 3. What would we get? Well, we're going to get 3/4 to the power of n, so if n is 3, that's 3/4 cubed. And now we've got cosine of 180 times 3, so that's cosine, again I put the brackets in, I'll keep them there this time, of 540 degrees. Okay, I'm going to put it back in here, just to keep it consistent. And if we evaluate this, well, cosine of 540 degrees is -1, so what I get here is minus 3/4 cubed. Okay, so I get minus 3/4 cubed. And let's just do one more term just to see what's happening here. If I say n equals 4, then what I'm going to get is 3/4 to the power of 4 times cosine of 180 times by 4, it's giving us 720 there. Okay, and again, if we evaluate this on our calculator, this part here, the cosine of 720 degrees, is equal to 1. So what I get left with then is just simply 3/4 to the power of 4. And hopefully a bit of a pattern's kind of emerging at this point now, and this is why I always say just try the first few terms. Usually when you put the first few terms in, you can kind of see the pattern that's forming. So if we say n equals 2, we said that was either 9/16 or 3/4 squared. For n equals 3, that's minus 3/4 cubed. And then for n equals 4, that's 3/4 to the power of 4. So hopefully what you can see here is we've actually got a geometric series. So we've got a geometric series. Where the first term is 9/16. But how do we identify the common ratio here? What do we times each term by to get to the next term? Well, the way to look at this then is if you've got 3/4 squared, that's the first term, and then the next one is minus 3/4 cubed, and then the next one from here is 3/4 to the power of 4, then hopefully what you can see here is that we need to times by minus 3/4. Okay, the power is increasing each time by 1, so clearly we're just timesing each term by 3/4, but the sign is alternating between each one. Okay, so we times it by minus 3/4. So therefore, the common ratio R is minus 3/4. over 4. And because we're looking for this summation to infinity, then we just need the sum to infinity here for a geometric series. So the formula for this, quite straightforward, is just a over 1 minus r. So therefore all I need to do now is substitute a and r into this formula here. So a is 9 over 16, so that's 9 over 16, and we divide this by 1 minus r, where r is minus 3 over 4, so minus 3 over 4. And at this point now, we just evaluate this on our calculator. So I get 9 over 16 for the numerator. The denominator here is 1 minus 3 over 4, so that's 1 plus 3 over 4, and 1 plus 3 over 4, well, that's the same as 4 over 4 plus 3 over 4, giving me 7 over 4 there. At this point, just put this into your calculator. You don't need to calculate this by hand unless you really want to. But what you get here is 9 over 28, which is exactly what we wanted to show here. Okay, so that's as required. And that gives us our solution there to question 13. So that brings us to the end of this paper and the end of this video. Hopefully you found this paper and this video helpful in your revision. At the date of recording this, you've got a few more weeks yet to your first day exam. I think it's about 4 or 5 weeks. So there's still plenty of time. As always, I'd love to hear what you thought of this paper. You know, the questions, the difficulty, any questions about any of the questions at all. Like always, just leave a comment down below. But any feedback overall would be massively helpful for putting together paper 2 and the applied paper 3. Okay, so thanks for watching, and I'll see you on the next predicted paper.